Good morning or good afternoon. The next topic that we're covering in Algebra 2 is linear inequalities. And as with the last lesson, I am going to try to split this one in two to allow us more time to digest the information. I guess one of the advantages of meeting every day for a shorter amount of time is it allows us to space the information out more, so you get a chance to really digest what we're doing in one class before we add on to it. So to begin with, what is an inequality? Well, an inequality in math is one of these symbols, which of course did not draw very well. Let's try again. That would be our less than symbol, and then you could have less than or equal to. That just means that the equals counts as an answer. Think of it as like you have an equal symbol and then the top part of it becomes the inequality, like that. So the bar underneath it is like the bottom of the equal sign. I'm sorry, there's a cat howling outside this room while I'm recording this. Hopefully you guys can't hear it. And then we have greater than, and of course greater than or equal to. And then this one, which I think I put up on the screen earlier, is not equal to. And that one typically we don't mean most of the time. This is all one symbol. So whether it's facing this way or this way really doesn't change what the symbol is, because we always read from left to right. If you have something like this, you would read it 2 is less than 3. Again, remember it points to the smaller number and opens to the larger one. If it happened to be reversed, though, you would read the same symbol as 3 is greater than 2. And that's just because you're reading from left to right all the time. So I don't want you to think of it as two different symbols, like there's a greater than symbol and a less than symbol. It's basically just the inequality symbol. And because you read from left to right, you make sure it's pointing in the correct direction for whatever it is that you're writing down. Now, here's the key idea, and I want to emphasize this. This is going to come in very important when we do systems of inequalities, two-dimensional inequalities, and systems of equations. This idea, when we graph solutions, so we do a lot of graphing in algebra, we shade the answers. So what I would like you to do, if you're taking notes at home, if you're watching this on your own, is make sure you write that down. When we graph solutions, we shade the answer, we color it in, whether we're doing it on a number line or we're doing it on an XY plane. The idea is we shade in the values of the variable that are going to make our expression true, or our equation or inequality true. So I'm going to start with these, kind of a weird example. Suppose somebody asked you to graph x equals 2. Which is a really weird request. Typically you get x equals 2 and you're like done with the problem. But let's say that the question is asking you to graph it. Here's what we would do. We would take our number line and we would locate the 2 and we would shade in the 2. And we would do that by putting a dot. So we're kind of coloring in where the 2 is. It seems weird and redundant, and honestly, in this problem, it's not very helpful. But the idea is really helpful. Let's look at a related problem that's maybe a little bit more interesting. Let's say it was x is less than or equal to 2. Okay, so now any number that's less than 2 would be a solution. So that would include the 1, that would include the 0, but don't stop yourself there. That would include 1/2 and 1/4. It would include negative numbers, would also be less than 2, so maybe -1, -2. Anything less than 2, so 1.5, 1.8, 1.9, and also because it says equal to 2, we would shade in the 2. Now, it's not very efficient for us to do lots of these dots. So what we will typically do is we'll just kind of make a little squiggly line indicating that we are shading. But it's the same concept as the line above. We shade in anything that makes the expression true. Last one. Suppose it was just x is less than 2, but no longer equal to. So this one, we have like x is equal to 2, so we put a dot at the 2. Here it's less than or equal, so we're throwing in all those values that are less than, but we're still keeping the equal. How do we graph it when it's not equal? Okay, so let's, you know what would be helpful is if I knew how to count. Let's try again. Okay, so in this case, all of the numbers that are less than 2 would work. So that would be all of these numbers down here are all less than 2. I'm still less than 2, even though I've gone greater than 1. Here's where we have the problem. I can put in 1.9, 1.99, 1.999, 1.9999. And what I want you to get here is the idea that I have to get infinitely close to that 2, but not the 2 itself. So we can go like 1.99999999999. So we need a way to be able to mark the 2 as the end point. We need to be able to indicate on our diagram that it's everything up to the 2, but not the 2. And the way we do that is with what's called an open dot or an open circle or an unshaded circle. And then we would shade everything else. We have to put a dot or a circle at the 2 because that's the end point. That's where we cut off all the acceptable values. And the way we indicate that it's everything up to the 2 but not the 2 is by not shading it in. So many times I have students that struggle to remember whether or not they're supposed to shade in the circle because somebody gave them a rule and didn't explain the rule. So this should make sense to you. We shade the answers, whether it's a single answer like x equals 2 or whether it's a range of numbers. The idea is that we shade all the answers. If you need to mark an endpoint as not being a solution because you lost your equal to, that's why it's unshaded. That's why we don't shade in the circle. So if that's something that you had previously learned but never really had explained to you, I hope it makes more sense now that it's logical. And the same concept is going to work when we start doing this on the XY plane, the idea that we shade in the answers. Okay, so the nice thing about doing inequalities, linear inequalities, is that they're exactly the same as equations, except with one little catch. So here's a linear inequality. I have -3 times parentheses 2x minus 5 plus 1 is greater than or equal to 4. And the goal here is going to be to solve it and then graph the solution. And I'm going to try to explain to you the one little catch. So if you think back to our last lesson, I gave you some steps for solving a linear equation. Those steps work exactly the same way for linear inequalities. So the first step, to review, was clear any fractions. Yay, no fractions. I didn't want them in this problem anyway. Second step, simplify each side separately. When by each side, what we mean is each side of the inequality. The right-hand side is already simplified, so I'm not going to touch that, but I'm not going to forget about it either. Over here on the left, remember simplify means distribute and then combine like terms. So I'm going to start off with distribution. I'm going to take the -3 and distribute it through the parentheses. -3 times 2x is -6x. -3 times -5, a negative times a negative will give me a positive. Everything else is just going to come down. Like, get your structure nice and tight here. So bring down the +1, bring down the inequality, bring down the 4. Next step in simplifying is to combine like terms. I have a term with an x and I have two constants. These two can be combined. 15 plus 1 is 16. Next step is get the variable on one side. Well, we're already there because I only have the variable on the left. I don't have the variable on the right. And then the last step is to solve the 1 or 2 step, in this case, inequality. So we look at the x, we want to figure out how we get the x by itself. I have two things happening. We're multiplying by -6 and we are adding 16. The last thing done will be the first thing undone, which means we will subtract 16. Bring down the -6x. 16 minus 16 is 0. That's why we're subtracting 16. Now bring down the inequality, and always be careful with your negatives and the operations on the sign there. 4 minus 16 is negative 12. Now here's where we get to the step that is a little bit different with an inequality than with an equation. We want to get the x by itself. We know that this is multiplication, and we know that we can undo multiplication with division. We're multiplying by a negative 6, so we will divide by a negative 6. So far, so good. Negative 6 divided by negative 6 is 1, leaving me with just the x. Over here on the right, a negative divided by a negative is a positive. 12 divided by 6 is 2. Here's the extra step. When you divide by a negative, you have to flip the inequality symbol around. I'm going to make a little note there that says flip. So there are two mistakes that students will make with this. One is they will not flip the inequality when they are supposed to flip the inequality, and the other is they will flip it when they're not supposed to. So here's the rule for when you flip your inequality. You are going to flip the inequality when you multiply or divide both sides by a negative. I used to just say when you multiply or divide by a negative, but that does not apply if you are distributing a negative. I had a student once ask me, well, here you're multiplying by a negative, shouldn't I flip the inequality around? And I realized that no, that's not exactly what I meant. It's when you divide both sides by a negative. Honestly, division will be a lot more common than multiplication, but remember that dividing and multiplying are really the same thing. Division just means you're multiplying by the reciprocal, so it does apply to both. So explaining this is tricky because what happens when you're operating with that negative that you should turn it around. So I'm going to give you just an illustration. This is not a definitive proof of anything, but suppose you had this inequality. Negative 6 is less than positive 12. Hopefully that's clear. Now what I'm going to do here is I'm going to divide both sides by negative 2. So this would fall under that dividing both sides by a negative. When I divide a negative by a negative, I end up with a positive. So this side over here becomes a positive 3. And when I divide over here, a positive divided by a negative gives me a negative. So this ends up being negative 6. And what you can see here is that the order or the magnitude of these have changed. Now I have a positive on the left and a negative on the right. And so the inequality would have to go that way. Positive 3 is greater than negative 6. This is about the clearest way that I can show you why that happens. It also works with like numbers that might both be negative. So I can show it to you with positives and negatives. But let's say you had something like negative 3 is greater than negative, not 5. Let's do negative 6. Okay, now that's harder to see because we're dealing with negatives, and negatives just make things a little bit harder to see. But negative 3, we'll say it's not as negative as negative 6. So if you look at your number line, here's the negative 6. The negative 3 would be over here. Okay, and you can tell that the negative 3 is actually greater than negative 6 because it's further to the right on the number line. If I take both of these and I divide them by negative 3, no, let's actually do that differently. Let's do a multiplication one. Okay, so let's multiply by negative 2. I'm going to multiply both sides by negative 2. I don't know why I put all those extra parentheses in there, but we have the same thing happening. A negative times a negative would give us a positive. And over here, a negative times a negative would give us a positive, and 6 times 2 is 12. And notice what's happened now. Instead of having a greater than symbol, we actually need a less than symbol because 6 is less than 12. So that's hard to really explain why you have to flip the negative there, but I hope that makes it a little bit clearer. So when you're doing a problem like this, when you realize you're dividing both sides by -6, you do need to flip that inequality around. And then we have x is less than or equal to 2. I'm not going to bother graphing that because I graphed it over here, so we won't beat a dead horse, so to speak. Let's take a look at another problem. So we've got -2 times x plus 9 in parentheses plus 5 is greater than or equal to 3. I'm going to pause this in the actual presentation and we will talk about it together. And then if you're watching this video later to make up for missing the video, or you just want to watch it again on your own for another explanation, I will go through a pretty quick explanation on the video as well. Okay, let's take a look at this. So we would solve this with the same steps for solving equations. So clear fractions, no fractions. So we're going to simplify each side. And I'm going to do that by starting with the distribution. Again, you don't have to do the arrows. Okay, I'm just doing them to illustrate the step that I'm doing. Remember that you have a negative times a positive, which is going to give you a negative, and you could write plus -18 if you wanted to. Bring down the plus 5, bring down the greater than, bring down the 3. Next step would be to combine like terms. Well, I have a -18 and I have a positive 5. That's -18 plus 5, which is going to give me -13. Bring down the greater than, bring down the 3. Anything you're not using is going to come down. That's your good technique and structure to your problem. And then the last step here, we will solve the equation, or in this case inequality, to get the x by itself. So we will add 13 to both sides. And you don't have to show this either. You really don't. In fact, there are math teachers here at AC that if you show that, they will get pretty upset with you because it's considered thought process, not actual work. So you could go straight from this line to this line, and I'll start doing that as well. Then we divide both sides by -2. If the number you're dividing by is negative, then you would flip it. -2 divided by -2 is 1, and we have to flip that around, and 16 divided by -2 is -8. If you are asked to graph that, here's all that I would expect you to do. The only number you really care about on the number line there is, wait a minute, hang on. Okay, I caught my mistake. It's a good thing. Okay, I think everything is okay. It less than or equal to -8. I think everything is okay there. Now I'm second guessing myself because what I have in my notes is not what I have written down here, and so that always unnerves me. All right, so anything less than -8 is going to be to the left, and it does have that equal to, so when we get to the -8, we are going to shade in the dot. Let's do one more practice. Let's do 2x plus 4 is greater than x. No. You guys are going to hate me for doing this in the video. Sorry, guys. Let's do 3x plus 4 is greater than x plus 6. And I'll give you a moment to write that down and work on it. We'll talk about it together in the live sessions, and I will work out the solution for those of you watching the video afterwards. Okay, step number 1, clear fractions. We don't have any fractions. That's good to know. Step number 2, simplify each side separately. So I look at the left and I look at the right and I try to find out if there's anything I need to simplify. There isn't. Okay, 3x plus 4 is as far as I can go. X plus 6 is as far as I can go. Now we actually do have this step where you need to get the x on both sides. So I wanted to do this example just so we could work through that. Over on the left-hand side, I have 3 x's. Over on the right-hand side, I have 1. The easiest way to get rid of that is to subtract the x from both sides. 3x minus 1x is 2x. Bring down your plus 4. Bring down your greater than. X minus x is 0. And then I am left with the 6. Now I should have a 1 or 2 step inequality. In this case, it's a 2-step. Subtract 4. So 2x is greater than 2. And then we will divide both sides. Now don't flip the inequality. Remember, you only flip the inequality if you're multiplying or dividing by a negative. And so I end up with 2 over 2, which is 1, which is x, is greater than or equal to 1. The only number that's really important to have on your number line there is the 1. And we're looking at anything greater than or equal to, so we would shade it in. And that's a wrap. I know I ended up second guessing myself. I think there's a mistake in my handwritten copy of the notes, and then when I realized that what I'm writing on the screen doesn't match what's in the copy of the notes. So that got a little bit bumpy in there. Hopefully you're okay with it. If I did make a mistake, somebody's going to call me out, which is totally fine. So we'll get that out of the way. If I do something wrong in a lesson on the board, please say something. Don't assume that just because I'm the teacher, I don't make mistakes, because I absolutely do. And I take them as a teaching opportunity to show you guys how to handle mistakes and how to go and fix mistakes. So please don't hesitate to say, Miss Taylor, I think you forgot how to add. Okay, just let me know. All right, so we will move on to the next topic in the next lesson.